Okay, so now I know I was cut off in the middle of where the last video ended, and I just kind of want to recap. We were talking about sound intensity. Okay, sound intensity is something that deals with as sound propagates out, that goes out in kind of a spherical sense, and we're looking at how it's related to the radius. Back up. Here. I apologize. There we go. And we'll see how sluggish our machine is today. It relates back to the radius. Okay? And so as we get further and further away, the intensity of that sound decreases. Okay? So if you're really close to the speaker, it's really intense, but if you move back away, it's a little bit less. Typically when you buy like stereo speakers are rated for a power output, okay, or there's so many watts, so like you're given like a 5,000 watt speaker, and so that wattage is something that we're given there, and that's all geared based upon how close you are to, based on the being right next to the speaker. Again, that sound dissipates or it loses some of its energy as it kind of gets further and further away. And we were talking about how the threshold of hearing is 1 times 10 to the negative 12th watts per meter squared. Okay. Again, when we start to talk about sound intensity, we talk about that sound intensity in terms of decibels. Okay. And really, when I look at the word decibels, I'm going to kind of highlight this. It's the unit bells. Bells is what we're talking about. Deci just means that we have 10 bells equal to 1 decibel, okay? And so we start to relate it in terms of that prefix in the metric system, okay? No, it's 10 decibels in 1 bell, okay? Because it's like centi is 100 and deci is 10. All right, so it's one place where we use that. Ideally, we find that if we're at 120 decibels, that's kind of the threshold of where we want to be pain-wise. Okay, if you hit 120 decibels with no ear protection, you can manage it for a short amount of time. So again, a lot of this is dependent upon the length of time that you are experiencing this. Okay, so you might experience a noise that's going to give you a high number of decibels. But if you're only experiencing it for a short amount of time, it's okay. Your ears are probably going to ring, but eventually you're not going to 100% harm your hearing. As you go with more extended periods of time, that's what actually hurts your hearing aid or creates hearing loss is the extended amount of time. So again, it's a time versus intensity relationship. Now, there is a kind of this mathematical relationship to this whole thing. And the mathematical relationship, of course, is this relative intensity is equal to the ratio of like our power output. Okay, so like our speaker wattage versus an ideal wattage. I kind of like to think about this in a little different sense because we tend to see more, at least in this class, the intensities actually given in watts per meter squared. But again, it's a relative thing because it's all relative to that propagation. That propagation is spherical. Okay. So I like to look at it in this, where this is the intensity that's given, and this is the threshold of hearing. And so then you find the ratio between the two, and then you take the log of those two things. Okay, so it's log of that. And then to get it into decibels, you just take it times 10. So if we left it without the 10, that would be in the units bells, but with the 10, it's now in decibels. Okay, so that's kind of how we're going to go through and do that type of thing. So again, if I look at something that would be, I'll do an example problem in class. Okay. Now we get into kind of the more fun stuff, and I'm going to do some demonstrations that are going to deal with this, but this is when we get into this thing called resonance, okay? And resonance is kind of that key thing where we're looking at how we can get everything to vibrate. And this is kind of a big thing. everything has the ability to vibrate, okay? And for those of you that have never done this before, this is a good thing to do at home. Go ahead and get a couple of those little like styrofoam cups or plastic cups and that, and get some string, and you take the string and you tie knots in it, and you poke a hole in the bottom of the cup, and you basically make the string foam cups, okay? Those work well. The one thing that you have to do with that string is the string has to be taut. It has to be tight. You have to make it so that it can actually carry that vibration sound. But you can talk in the one end of the one and one end of the other, and so if you get a really long string, you can create that. Now, the moment that string hits like a wall or something like that, that's where you get into that dampening effect, because again, that vibrating string energy will transfer part of that energy into the wall, so you have to be careful about where that string is touching. But that's something that we can look at. So we can force anything to start to vibrate. So when you talk into the cup, you're forcing the air molecules to start to create that longitudinal pattern, which makes the bottom of the cup vibrate, which makes that string then forced into a vibration. I have a nice picture of a guitar, okay? And this is really the part of the guitar that I like to look at the most, okay, is this part right here. This is that opening area where you have kind of like a sound chamber, and then the rest of the guitar is just there to catch sound and re-vibrate it, okay? And so what you're doing when you strum the strings on the guitar is it actually forces the air, okay, around that string to get into that little longitudinal pattern of compressions and rarefactions, okay? But there's not a lot of air molecules that are doing that. Eventually, those air molecules get inside of that chamber, and it makes the air molecules inside that chamber vibrate too. And so you get a forced vibration, okay? And we call that resonance, okay? So it makes all of the air molecules inside that big chamber vibrate, and then all that rich sound comes out of there. We do the same thing with the piano. A piano has a soundboard inside of it, so there's an actual soundboard in the back by where the strings are, and so then it forces it to catch it. And I'll show a demo of that in class as well. Now, when we look at strings, and as strings start to vibrate, we look for wave patterns, okay? And this is our basic wave pattern. So if I said this from here to here is a length of string, and it vibrates here and comes back here, we get one kind of half of this wavelength. So we got to think in terms of kind of like that crest trough thing, where this would represent the up and then the down, and that gives me one wavelength. Well, in this particular case, a wavelength here is equal to 2 times whatever the length of that string is, okay? And that's what we call the fundamental frequency, okay? It's the fundamental wavelength of this string. So every string has the ability to vibrate at a fundamental. Now, typically, if you were to take a guitar string and you pluck it, you won't see just that one pattern. You'll see multiple patterns within there. And that's why, you know, the different stringed instruments will give us a kind of a richer quality sound. We call it timbre, okay? A rich quality in sound is called timbre. And that's because you see all those wave patterns adding together. And it's all these different harmonics. So we're actually playing multiple harmonics on the same string. So in other words, that same guitar string, which is the same length, may get a pattern that looks like this. And so now this pattern fits in there, and we can see that in this particular pattern, your wavelength is represented by the length of the string. Okay, we call this then the second harmonic. Okay, so this is our first harmonic, this is our second harmonic, but it's our first overtone, okay? And an overtone is what we build into all of these sound patterns, and so all these sound patterns feed together to give us the rich sound that we expect to hear from a guitar. And it's different than, say, from a violin, okay? So again, if you played the exact same note, the same frequency, okay, like a middle C, on all the different string instruments, each one would give us a different wave pattern based on these different harmonics that we're seeing, or these different overtones that we're seeing. When we look at this picture right here, you can see now that we get one wave there, plus we get this other half a wave. So we're actually a wave and a half in this length. Okay, so this length now represents 1.5 wavelengths. Okay, and so you can start to relate to the fact that we're getting more and more. We can squish more and more waves inside of here. This one is actually 2. Okay, and so we can continue doing that, and that's typically what we see when we pluck the guitar strings, is we see all these different vibrations at the same time. It allows us to kind of figure out things, but for most of our calculation points on the problem set, we're probably dealing most with the fundamental, or they'll say it's the first third harmonic, or the first harmonic, or it's some multiple of the fundamental. Okay, and so we'll look at that. When we get to other musical instruments, most of those instruments were vibrating something. Again, you cannot produce a sound without a vibration of some sort. Bringing back, I wanted to just pop back here once here. When I was talking about a resonance and that forced vibration, I had to pull the video of the Tacoma Narrows Bridge in Washington. And that bridge actually had a forced vibration. It created resonance. The wind blew over it, just like you would blow over, say, a reed or something like that in an instrument. And it started to it vibrated at its natural frequency, and then it built upon it, and we saw it intensify it. And that was something that we looked at in a video form, and it happened years ago, and that bridge actually collapsed because of that. And so that's a good link to go look at it when you're done with this video. All right, so now back to our air columns. So most of our instruments, we blow into them. Okay, so you've got a trumpet, you've got a tuba, you've got a trombone, you've got a clarinet, a saxophone, an oboe, flute. They're all considered these tubes that we blow air into. Okay, and we blow air into the one end, and the other end is where the air exits. So they're considered to be an open tube. And these are what we would look at as open tubes. Okay, so these open tubes are how we look at sound. Now again, when we start to say what's the smallest part of a wave that can fit in there, we get this one being our fundamental. Now in here, we're seeing this part of a wave. This is actually half of a wavelength that's fitting inside of there, and it's vibrating. The difference when we get to this is that it looks like a transverse wave, but really it's about pressure differences. We see a high pressure and we see a low pressure, and there's those high pressure, low pressure, high pressure, low pressure, and those changes in the pressure are what cause us to have different sounds. So in other words, we have low pressure here, we have low pressure here, and then we have a point of high pressure in the middle. Okay, very similar to our nodes and antinodes. So when we blow over the end, we create a pressure difference. There's a point of low pressure here, and then all of a sudden we get this intense pressure in there and a low pressure there, and that's when we get our wavelength. When we go through our tubes, we can see that we can get a full wavelength, we can get 3/4 or 1.5, we can get 2, we can get 2.5. We're getting all multiples, okay? All multiples of this, which gives us all of our frequencies. It goes right back to what we were looking at here in our strings. We get all of our harmonics, all of our overtones are possible on a open-ended tube, so we can get all of them. Now this is exactly why every instrument that we play is a set, is made of an open-ended tube, okay? Because we can get everything. Now by changing the lengths of our tubes, that's what gives us different frequencies as well. So changing the lengths will get us different frequencies. That's what a trombone does. You change the length. When you press the keys on your trumpet, you're actually forcing air into different length of tubing. So you're getting different lengths of tubing to produce different ones. You'll get different vibration patterns, and again, that gives us the different qualities of sound. It gives us a difference in timbre. When we look at a closed tube, okay, so now a closed tube is like your pop bottle. Okay, so you blow over the end of your pop bottle. That air is forced to come out the same hole that you're blowing into. Okay, so you're creating a pressure